In this chapter, we're going to study the mechanics of fluid. Before we study that, let's first take a general look at what's called states of matter. What is a particular state of matter? Can you give me an example? Well, in fact, as you know, for most objects, for example, water, H2O, depending on the temperature, there are different states: solid, liquid, gases. These are the three most common phases. And there is, in fact, another less common known one, which is called plasma, that exists at very high temperature. What is a state of matter, or a phase of matter, that is? Well, a particular state or phase of matter refers to the way the molecules of that matter are congregated together. For example, in the case of a solid, the molecules are tied together with a fairly strong intermolecular attractive force, so that they're not allowed to fly apart. The best each molecule can do is to wiggle a little bit or vibrate a little bit around its equilibrium position. It is not allowed to fly away from each other. This is why a solid can hold on to its shape and its size as well. Okay, as you heat up a substance, the intermolecular forces become weaker because the molecules get more energy, so therefore they can overcome the intermolecular force so that they can start to slide past each other. Okay, there's still not enough energy for them to fly away from each other, but at least they can slide past each other. This is called a liquid. Since the molecules can slide past each other, what we have here is a substance that can hold on to its volume but not to its shape anymore because of the sliding between molecules. As the temperature gets even higher, the intermolecular force becomes even weaker, and each molecule has even more energy, and therefore they can fly away from each other, and what we have is a gas. Okay, to use an analogy, suppose I look at a class of students. Okay, let's say each student resembles a molecule. Then what is a solid state? A solid state is when this class is in session. Okay, so I'm having this class here. Nobody is going anywhere. Everybody sits in his or her chair. You can move a little bit around, but you cannot really, mingle around, stand up and walk around, and go out of the room, that sort of thing. That doesn't happen, right? So you're pretty much trapped to your chair, just like a molecule is trapped to its equilibrium position. That's called a solid. Okay, so what's a liquid? Well, in the case of a liquid, the molecule can slide past each other. And to use the human analogy, what we say is that each student, you're not having a class anymore, rather you have a party, okay? So the door is still closed, the molecule is not getting out, but you can slide past each other. You can go from one part of the room to another, no problem, all right? What about a gas? Well, a gas, if you use a human analogy, this is just like the class is over, open up the door, everybody gets out. That's a gas. Okay, plasma, that happens at very high temperature. For example, for water, it happens at thousands of degrees of Celsius. And this is the case where the temperature is so high that the positive and negative parts of the H2O molecule are taken apart. Okay, so what you have here is a collection of positive and negative ions in a very hot soup. That's called a plasma. And we usually don't deal with that because it's not a very common state of matter. Usually we deal with the three common phases: solid, liquid, and gas. Okay, now when it comes to solid, we know solid can take on only a certain shape and certain size. Liquid and gas, on the other hand, they don't have a finite shape and size. In the case of a liquid, the shape of a liquid depends on its container, right? In the case of a gas, it also depends on the container. This is because there is something different between solid and the other two common phases, that is liquid or gas. Whether it's a liquid or a gas, they both can flow. This is not something you can think of when you have a solid. Solids do not flow. Okay, so in this sense, we say a liquid or a gas, either one of them is called a fluid. Fluid is a substance that can flow. So we have something new here, a substance that can flow, and this is something we never considered before. And what is the mechanics of a fluid, which means either a liquid or a gas? This is what we study in this chapter. Okay, before we move on, just something out of fun. What about glass? Common glass. Okay, is this a solid? We'll say, why, of course it's a solid, because glasses do not flow, do they? Well, I'll tell you, if you go to a very old church in Europe, hundreds of years old, and you take a look at the glass window pane, if you take a closer look, then you might actually discover something interesting, and that is the bottom part of this glass pane is actually thicker than the top part. You know why that is the case? It's because glass, believe it or not, is actually a fluid. Okay? It is a very sticky one, however, and that is it's going to take hundreds of years for the flow of this very sticky fluid to be significant. So when you wear a pair of glasses, you're not going to worry about it deforming due to the flow of the glass overnight or over a few years, because it takes much longer time to do so. So basically glass is actually a fluid, but it's a very sticky one. Okay, it's just something for fun. Alright, now one of the things that we studied in the very first chapter of this physics course is density. Okay, density, as you know, by definition is mass per unit volume, and it is measured in prime SI units as kilograms per cubic meter. Another common unit is gram per milliliter or gram per centimeter cubed. Density is a very useful quantity when it comes to fluid mechanics, so let's look at some common materials. Okay, water, for example. What is the density of water? The density of water, as you probably know, is 1 gram per centimeter cubed, to a good approximation. Why such a round number, 1? Well, this is not a coincidence. This is the way we want it. How did we initially define 1 gram? That was defined as the mass of 1 milliliter of water. Then of course the density of water by definition is equal to 1. Okay, this is only approximate because it does change slightly as temperature and pressure changes. Okay, so that is the density of water. So every milliliter of water, that's a cubic centimeter. Okay, here is roughly a cubic centimeter. It's about something like this. Okay, it's about the size of a fingernail, all right? The size of this fingernail right here. This much water has a mass about 1 gram. Okay, another common substance is air. Okay, because air is a gas, and it's, of course, it's a fluid. It's a very common fluid, and therefore, let's look at the density of air as well. What is the density of air? Of course, you know, if I look at only a milliliter of air, it's not going to have much mass at all. Now, let's look at something much bigger. Let's look at 1 cubic meter. Okay, so imagine you have a big box, 1 meter by 1 meter by 1 meter, and you fill it up with nothing else but air. My question is, what is the mass of the air inside? How much does this air weigh if you put it on the surface of the earth? What do you think is a clever guess? Well, what do you think? If I say, per cubic meter, right, the mass, let's look at some possibilities, okay? Shall we say 1 gram? Okay, 1 kilogram, and 1 milligram. Okay, I have 3 choices. Let's say I'll give you 3 choices. Which one do you think is more likely? A gram occupying a whole meter cubed, a kilogram, or a milligram? Okay, which is 1/1000 of a gram. Well, we all know air is very light, and therefore we don't even feel it that much. So I would say most people would choose probably a gram or even a milligram, right? How many of you do actually think that should be a kilogram? That is more than 2 pounds of weight, okay? This empty box containing nothing but air, the air inside, would it weigh 2 pounds? That doesn't sound likely, does it? But I tell you what, the actual density of air at room temperature is even more than a kilogram per meter cubed. The density of air at room temperature is around 1.3 kilograms. That is nearly 3 pounds of air. Okay, just every cubic meter. This is astonishing. How come we don't feel the weight of the air? Well, I will show you why that is the case, and in fact this number can be used to calculate what's called the pressure of air, which is otherwise known as the atmospheric pressure, which we will study in detail. And speaking of pressure, you know, this is a term we use very commonly in everyday language. Okay, I'm under a lot of pressure, right? Now in physics, the term pressure has a definitive meaning. What does it mean? Suppose there is an area, surface area A, okay, and I apply a force perpendicularly on this area, F. Okay, what is the effect of this force? Suppose I want to know how likely is it that this area might be punctured, okay, the surface might be punctured. Let's say I apply, you know, a force on the floor. Does it crack the floor? Well, you know, common sense tells us that if you want to know the effect of that force in terms of whether it's going to break that surface or not, it is not just how much force we have to consider, but how big that area is, right? And that is, you want to look at how concentrated that force is over this area. For this, we define a concept called pressure, P. It is defined as force applied per unit area. Okay, so you have this force, suppose it's evenly distributed over this area A, then the pressure over this area caused by this force is called F over A. So basically, it is the concentration of force per unit area. The SI unit of that quantity, pressure, is Newton per meter squared. We give it a new name. It is also called Pascal, or PA. It's named after French physicist Pascal, whose name will appear many times in this chapter. So 1 Pascal, by definition, is 1 Newton. An interesting application of the pressure concept is the comparison between the pressure produced by a foot of an elephant and that produced by the high heel worn by a woman. Let's assume that we're looking at an adult elephant that weighs about 16,500 pounds. That is very heavy. That corresponds to a mass about 7,500 kilograms, or roughly speaking, a weight of 75,000 newtons. Now, we know the elephant has 4 feet, and each foot has a different size footprint depending on what kind of elephant we're talking about. Data shows that it ranges somewhere between 12.5 to 35.3 centimeters in diameter. So let's say, on average, let's say for simplicity, it's 25 centimeters across. Okay. How much is the pressure produced by the weight of an elephant on each foot? Let's see now. We have a total of 75,000 newtons. Okay, and we divide it by 4 to get the force exerted on each foot due to the weight. So that's 75,000 newtons over 4. And you divide this by the area, the footprint area of the elephant feet, and let's 0.25 meters, and I square it to get roughly the area. And what do I get? Well, it is a large number, all right, in Pascal, and if you work it out, you find this value to be about 300,000 Pascal, or 3 times 10 to the 5 Pascal. All right, while this may sound like a lot, let us look at the pressure produced by the high heel worn by a woman. Normally speaking, when she walks, the contact area between the shoes and the ground actually has 2 parts to it. One is the heel itself, and of course there is also this part. But for a moment, let's assume that she momentarily lifts off this part off the ground so that only the heel itself is touching the ground. I want to know what happens at that moment. The weight of the woman, let's assume it's only 100 pounds, okay? And there are, of course, 2 shoes, so each of the 2 heels would get about 50 pounds. So you got 50 pounds, that's about 500 newtons, right? And you divide this by the cross-section area of the heel. Now, that of course varies from shoe to shoe, but let's look at an extreme case where you have a very small area. Let's say it's like a centimeter across. I mean, there are heels like that. Okay, that is 0.01 meters. And you have to square it, right? Okay, what do we get? What we get is a very large number. All right, let's make a little correction here. The force is about 50 pounds. That's not quite 500 newtons because 1 pound is roughly 5 newtons, so we have to divide this by 2. It's more like 250 newtons. But still, you take 250 newtons over the area of 1 centimeter squared, the number that you get is still astonishing. Okay, it's 250 over 0.01 squared, so that's 4 extra zeros. What do we have here? That is 2.5 times 10 to the 6 pascals. All right, we compare the pressure produced by the foot of an elephant and by the heel of a woman. You can tell, okay, this is nearly 8 times. It's about 8 times as much as the pressure produced by an elephant foot. So it is not just the force that matters, it's also the concentration of the force. The high heel having such a small contact area with the ground produces a tremendous amount of pressure, 8 times that produced by an elephant, and so it can really hurt. All right.